Okay, it's my pleasure to introduce the guest lecturer in the finite and algorithmic model theory theme, Atserias, who will be telling us about logic and random structures.
Thanks. So I'll tell you about logic and random structures, and maybe I should be calling it random graphs, because mostly I'll be talking about graphs. Maybe at the end we'll say something about structures, but most of the focus will be graphs. So here is the random graph papers, the classics. We have Erdős-Rényi and Gilbert. So Gilbert is not as well known, but many people do know the story that Gilbert was the one who introduced the so-called GNP model, where you throw edges in the random graph independently with probability p. Each edge appears independently of the others. In the Erdős-Rényi model, instead, what they were considering is the uniform distribution over all graphs with exactly m edges, or n. They were using capital N. It turns out that these two models, for most of the interesting things, happen to be equivalent, and very often one switches from one model to the other in order to prove certain things, and then apply some general theorems that allow you to go from one place to the other. So for us, we will focus mostly on this model, which I'm going to define now. But before I do that, I want to, a little bit of history. I wanted to know why these people consider random graphs. And well, Gilbert was working in Bell Laboratories, and then you start reading, and it starts like a mathematical paper. So let n points numbered 1 to n be given, blah, blah, blah. But then you go a bit further down, and there is this paragraph. You cannot really read it, but I can read it for you. And it says, as an application, imagine the endpoints to be n telephone central offices, and suppose that each pair of offices has the same probability, blah, blah, blah. So really, I don't know if he had this motivation, but at least he had this written here, maybe to please his boss. I don't really know. So in both cases, they were studying the probability of the random graph being connected. And however, the focus of Gilbert was more in the case where p was a constant, and therefore you have a dense random graph. And Erdős-Rényi were more interested in the case where the number of edges is very sparse, is very small. So something like n log n. It's not very small, but relatively small. And these two things will be actually leading through my talk, and so I will talk about them when it comes the time. So what are random graphs and what are limit probabilities? How do we define them? So you have, let's say, Gn is the set of all indirected graphs, and we're considering labeled graphs with labels 1 to n. And G is the union of all graphs on these vertices. Now, G and P is a discrete probability space, which is defined because it's finite, you can define it on all points and then extend it by sums. So every graph gets this probability of appearing. So P to the number of edges, independently each edge appears with probability P, and each non-edge has probability 1 minus P of being a non-edge. And then when you have a set of graphs, you define each probability to be the sum of the graphs that are in the set. Now, when you have a set of graphs, you want to look at the limiting of these probabilities. And then you look at the mu of p. We denote this as the limit of all these probabilities at the finite stages when the limit exists. So what are questions that we can ask in this model, and what Erdős-Rényi and Gilbert asked? So things we can ask is, well, for which p's or which properties of graphs does this limit actually exist? So this is the first question we want to ask. Then what kind of shapes this function, so this gives you, for every n, it gives you a probability, which is the probability that the random graph with n vertices satisfies the property. What shapes this function can have? That's another question you want to ask. What convergence rates do you have? Can you answer these sort of things? What are the almost sure properties of the random graph? Almost sure would mean that it's a property that holds with probability 1 as n goes to infinity. We're looking at asymptotic combinatorics, so we're looking at the asymptotic limit. How do we compute the probability, the limiting probability when it exists? And for us, what we're interested in is, can logic shed light on such questions? And if you look at the literature on random graphs, there is always some logical component behind, because The properties that people are interested are very uniform, usually. They are definable, they are certainly uniform. There is one exception that I will talk about in the end. So they are defined by some finite sentence of some language. And on the other hand, they are also usually closed on their isomorphisms, so it makes sense to talk about what is their logical complexity, what does it take to define them, and therefore it makes sense to ask what logic can say about it. So the first part of the talk, I will talk about the dense case. The dense case means that the probability is fixed. It's going to be a constant. It's 1/2. It could be any other constant. The same theory would go through. What this means is that the number of edges is approximately half. On average, right? It's half of the number of possible edges, and you have so therefore you have n square edges more or less. So here's a basic tool that we want to use when we want to do counting and probability, which is the inclusion-exclusion principle, and this is a very basic thing we learn in kindergarten, I guess, but it turns out that we never need the full power of this. This is quite powerful if you use it if you're able to use it completely. You usually only need the union bound, or the first moment, as it's sometimes called, and the second moment is often enough to get all your estimates that you need. So these are called sometimes the first moment and the second moment. So you notice that this is an upper bound, this is a lower bound, and in fact any two terms and then two consecutive terms sandwich the right set. Size of the set. So one thing is that when you study random graphs, you realize that this is happening, you're using these things over and over again. And mostly especially in the dense case, you don't use many more things. Basically, this is all you use. So by analyzing what logic can say about random graphs, we will find out that this is also the only thing we need. And it will be a justification why it happens that in the theory of random graphs, this is always the thing we're using. So let's see several examples, and let's see our point at the end, how it is justified. So let's compute this very simple probability. All points have at least one neighbor. Well, let's look at this event. For a fixed n and a fixed vertex, what is the probability that u doesn't have neighbors? Well, you have n minus 1 candidates neighbors, and if it's not a neighbor, you have 1 minus p probability, and these are independent events. So this is the probability of u not having any neighbors. Now, some vertex does not have neighbors. This is just a union, right, of these events. And therefore, you can bound it by the first moment. And so these are n times the same probability. So you can see now that if p is a fixed constant, then this is an exponential function. This is a polynomial function, so this goes to 0. So the probability that some vertex does not have neighbors goes to 0. So the probability that all points have at least one neighbor goes to 1. By the way, here I can illustrate the use of the second moment. If we use the lower bound using the second moment, then it's not difficult to compute these quantities. And then what you get is a very good approximate, because this quantity here goes to 0 very quickly. So you get a good approximation of this very simple case. I'm going to do 3 examples because they are illustrative, and they will be useful later. The second and the third one will be a bit faster. So all pairs have a common neighbor. Let's say 3 vertices are different. Let's say they are all edges. This is p squared, probability p squared. Now the probability that u and v do not have a common neighbor, well, not having a common, that w is not a common neighbor is this probability, and you have n minus 2 possibilities for different vertices, and these are independent events. So you get that. And then you apply again the union bound. You get a polynomial function, an exponential function, something that goes to 0. So we get what we want. So these are examples of what we call extension properties. And in fact, you can ask, can we go further? Since in the case p equals 1/2, you have a symmetry between edges and non-edges, you can ask actually more general questions like this. So let's say the RS extension property is the following. You want to say that every R set and every S set, there is a point that is fully connected to everything in R, and it's fully disconnected from everything in S. Okay, so green is supposed to mean edge, and red is supposed to mean non-edge. So this is the RS extension property, and it's not even clear that there are finite graphs that satisfy this. But if you do this very simple counting, they do. Most of the graphs actually satisfy this for fixed R and S. So let's do it again, very simple computation. So you have a set of size R and a set of size S listed as a tuple, what is the probability that all these things are edges and all these things are non-edges? You have P to the R 1 minus P to the S. So now, what is the probability that U and V fail to have an appropriate extension? So an extension of the right kind. Well, this is the probability that a particular candidate fails, and you have these many possibilities, and they are independent events because they involve disjoint edges. So now you take the union bound. What is the probability that some R or S tuples fail to have an appropriate extension? You get a polynomial function followed by an exponentially decreasing function, so this goes to 0. So we proved that with high probability, for every fixed R and S, the graph is going to have this RS extension property. So it means that any two sets can be extended any way you like, any sets of size R and S. So this is the concept of K-extendable graphs that was studied by Geifman as a property of graphs, and he was looking at the infinite graph that satisfies the RS extension properties. So let's say that the graph is K-extendable if it satisfies the RS extension for all R and S that add at most K minus 1. So it means that any K minus 1 points can be extended to another one in the way you like. So what we just proved is that the property of K extendability goes to 1, and that's because you have finitely many, for every fixed K, you have finitely many of these. They all have probability 1, so the conjunction has also probability 1, because it's a finite number. So this where the notion of extendability was studied by Geifman in the context of infinite models, and he wanted to define measures on infinite models. And but then these two groups of people, Fagin making a person, one group of one person, they realized that this property holds. Geifman did not state this explicitly. It's not clear that he knew. But this is true, and they made a use of it. So what use did they make of it? They proved the 0-1 law. By the way, these people here, so of course, these are 4 Russians, and Fagin was in America, so this is one more example of the separation between East and West. So they were not aware of their work. Fagin was aware of Geifman, and he states explicitly that it doesn't seem to follow from Geifman's work that this is the case.
I think Andreas has a paper, right?
Later.
Late?
Yeah, we talked about that. Yeah, Andreas has a paper as well on that. They also prove that. All right, so the 0-1 law, this is the use they made. So the 0-1 law states the following. It's a very simple condition. It says that if you have a first order definable property of graphs, then the probability is either 0 or 1. So it's that simple. So this answers already quite a lot of the questions we had in the dense case. It was what properties have limits? Well, all first order properties have limits. And what are the limits? Well, they are 0 or 1. It even answers things about the rate of convergence. And this is also Fagin's paper, and we actually follow from the proof that I'm going to give now. So this is Fagin's proof. It said the following. So let's look at, well, first of all, K extendability for fixed K is a first order formula. For every R and S points, there is a W that extends. So now you take this set of sentences, you take the sentence that says that the relational structure is a graph, the binary relation, symmetric and irreflexive, and you put all the extension axioms as they're called. All right, so this is a theory, and this has a countable model. There are 2 ways to see this. One is you build one explicitly, and there are several ways to build one. One is by extending finite sets and keep adding elements until you take the limit, and this will satisfy it. Or you can do it explicitly as well. There are explicit constructions, quite simple to do. There's another way, which is by using compactness. Because we just proved that these sentences have probability 1, any finite set of these is going to have probability 1, and therefore will have a finite model. So every finite set is satisfiable, so the whole thing is satisfiable by compactness. So this has a countable model, and in fact, this model is actually unique up to isomorphism. And this is exactly what Geifman was doing. Geifman studied the Rado graph, and he realized that this set of axioms imply that the theory of the Rado graph is omega categorical. So all models of the theory are going to be isomorphic. So in particular, it means that if they are isomorphic, the theory is complete. So it means that for every formula, either it's a consequence of t or the negation is a consequence of t. And now you apply compactness to this. You say, well, for every phi, there is a finite t0 that either implies phi or it implies not phi. All right, so, but now this is a finite set of things that have probability 1. So this is going to have probability 1. So you're left with the conclusion that we wanted, which is that the probability of phi is at least that of this, and the probability of this is 1, so the probability of this is 1, or the probability of this is 1, which means that the negation. So phi has probability 0. Done. This is the proof. It's very simple, very nice, and very clear. On the other hand, this proof doesn't say how do you compute the probability, how do you compute mu. But it's a very nice excursion into the infinite to conclude something about the finite. The 0-1 laws are really a property of a notion of finite structures. And in fact, it will reappear later, this kind of argument, if I have time to go through one of the proofs. All right, so how further can we go? We have this first order logic, and now we want to go to richer languages to express more properties. We already know from Anu's talk that connectivity, for example, is not first order definable. So for example, Gilbert paper, which was about connectivity in the GNP model for constant p, will not be explained by this, the probability of being connected. So let's go to richer languages. And just a little reminder from Anu's talk, let's recall that this denotes indistinguishability by k-variable sentences. So these are sentences of first-order formula that can be written, or first-order logic that can be written with at most k variables. And indistinguishability means that they satisfy the same formulas, sentences. And also from the lectures this morning, we know that inflationary fixed-point logic, so everything that is definable in inflationary fixed-point logic, will be closed under this equivalence relation for some large enough k. Well, k will be basically the number of variables it takes to write this inflationary fixed-point formula. Now, a crucial observation is the following. We were looking at the models of the k extension axioms. And it turns out that, well, if you look at all of them, then you get a single model, which is the Rado graph. But if you look at a finite number of them, or in particular a single one, two graphs are k extendable, then that is enough to guarantee that these two graphs are going to be indistinguishable by k variable sentences. And there is a very simple argument for that, which is based on the game characterization of this equivalence relation. So remember that two things are indistinguishable if duplicator has a winning strategy in the k-pebble game. And now, so let's see how we can use the fact that they are extendable up to k to design this winning strategy, and then we'll be done. So how is the winning strategy working? Well, at any time at any moment in the game, we have at most k pebbles on the board, right? In fact, less than k, because we're considering the case where spoiler now puts one more pebble. And duplicator has to reply to that, knowing that he already has a partial isomorphism between the pebbles that were before. And now he has to reply to something that spoiler pebbled, and he has to preserve isomorphisms. That's very easy. I mean, the new point is connected to some points and disconnected from others. So by the k extendability, remember we have at most k minus 1 things on the board, we have such a witness in the other graph. So duplicator will choose that and will continue the game. And this can go on forever as long as there are at most k pebbles on the board. So this is a very crucial and simple observation. It's saying that extendability up to k guarantees indistinguishability by k variable logics. But then this is very good because it has the following corollaries. Well, the 0-1 law for first order logic. Okay, and also for inflationary fixed point logic, and in fact for any class that is closed under the k equivalence relation for some k. So why is that? It suffices to prove the last one because the last one implies the others. This one will be closed under k equivalence and this one even more. So why is the last one true? Well, suppose you have a property that is closed under this k-equivalence relation. Now, this means that the property is made of a union of equivalence classes. But now there is one huge equivalence class that has probability 1, which is the one made of the graphs that are k-extendable. Right? So there are two possibilities. Either this contains the equivalence class of the k-extendable graphs, or it doesn't. If it does contain it, then it has probability 1. It has a huge equivalence class modeling the property. And if it doesn't contain it, then the complement contains it, right? Because it's closed under equivalence relation. So we get the 0-1 law. So this is a very simple proof now. Again, and it's different. It's different because it goes beyond, and it's not using the infinite graph. This is also quite important. So the history here is, of course, the 0-1 law was proved by Glebsky and others and Fagin. Then for inflationary fixed point logic, this was proved by Blas, Gurevich, and Kozen by a different argument, which was more, it was kind of a quantified elimination argument, which was more similar to this one. Maybe I'll say a bit more now. And then the last one was generalizing the others, was proved by Kolaitis and Vardi. And they were stating this in the language of infinitary logic, but for finite graphs or for finite structures in general, definability in this infinitary logic, which I don't want to define, is the same as being closed under this equivalence relation for some k. All right. Good. So we're going further. So now we know about connectivity. Connectivity is expressible in inflationary fixed point logic. So the probability the fact that it has probability 1 is explained by this. Well, of course, it's explained by many other things. Like two graphs are connected, 2 points are connected by a path of length 2. And this is true for any 2 points. So it's explained by, but it's saying something. So let's see what it's saying. So this is the notion of almost sure explanation. And I want to make emphasis on this because I think there is a story to tell here. So what do I mean by an almost sure explanation? Well, when you want to prove that something holds almost surely, it suffices to prove that some sufficient condition holds almost surely. Right? So if you want to show that it's connected, it suffices to prove that every 2 points are connected by have a common neighbor, for example. And a corollary of the Kolaitis-Vardi proof is that if you have a property that is closed under this equivalence relation and has probability 1, then there is a first-order definable explanation for it, in the sense that there is a first-order definable property that implies it and has probability 1. So it's a sufficient condition for property P, and it explains the probability 1. Why is that? Well, that's because you can always take as Q the K extension axioms that are enough to guarantee the probability 1. Remember, probability 1 happens precisely because there is a large equivalence class inside, which is given by the K extendable graphs. All right, so you have explanations like that.
Q entails P or P entails Q?
Q entails P.
Yeah. Oh, yes. Fine. Yes. Yeah.
So here's an example. All pairs have a common neighbor is a sufficient condition to connectivity, and we already argued that, by the way, this was the second example. All pairs have a common neighbor has probability 1. So this is an explicit explanation for connectivity. By the way, it also gives almost the right rate of convergence, but not exactly. But it gives a rate of convergence. So it says this converges to 1 exponentially fast, so in fact polynomial times exponentially decaying function. And Gilbert proved that this also goes, of course, but not faster than that. So this was the point. So this is why I call them explanations, because they not only they explain the fact, but they also explain more structural properties of it. I don't know if I'll have time to say more about it, but now I want to say an interesting non-example. So a non-example is the following. So you can ask, is every property that holds almost surely explained by some first-order property that holds almost surely? process like that, generally it's a bit hard to believe, right? But maybe you can explain Hamiltonicity, for example. And Blas and Harari prove the following negative result. It says the following. So if you take a first-order definable property that is sufficient for Hamiltonicity, it's a sufficient condition to guarantee Hamiltonicity, then you're screwed, it has probability 0. Well, of course, the relevant note here is that Hamiltonicity has probability 1. So that's why this is saying that there is no first-order property that explains Hamiltonicity and holds with probability 1. So this is a very nice negative result. It has a very nice construction. I want to describe it to you. It's the following. This graph, in fact, is very similar to Anus's graph. You have a k minus 1 click here, and here you have k minus 2 points. So you have one more point inside than outside. And what this is supposed to mean is that these points outside are connected to everything in the click. So you have a click, and all the points, satellites like this, are connected to everything in the click. You can also write it in a bipartite shape. You would say, you would put the satellites on the left and the click on the right. So you connect the whole click. These guys make an independent set, but they are fully connected to the click. So this would be the shape of Anus's graph. And now, because there are less satellites than the click, it follows that this is not Hamiltonian. And this is the same argument that Anus had, because in any Hamiltonian path, every outside vertex has to be followed by an inside vertex, but there are more.
You need it the other way around. You need more satellites than the call.
This should be k. This should be k. Thanks. It's a typo here. Okay, so you have more satellites than inside, and then that guarantees non-Hamiltonicity. Okay, so that by itself is not enough. Oh, by the way, what is the strategy to prove this? Well, I didn't say that. So the strategy will be the following. We're going to build a graph that is not Hamiltonian, but that satisfies enough k extension axioms. Right? So now the first order definable formula will be implied by some k extension axioms. So because it satisfies enough k extension axioms, it will satisfy the formula. But because it's not Hamiltonian, so either because it is implied it has probability 1, so it will violate this condition. That said, it's a bit wrong. So what I want to say is the following. So the graph will satisfy extension. Right? And so and this extension is enough to guarantee Q, because it's first order definable. Right, exactly. So if you had probability 1, then it would be implied by some extension. So G would satisfy this. But at the same time, we're going to show that G is not Hamiltonian. G that we construct is not going to be Hamiltonian, and then we will violate this. All right, so this is the strategy. But now we're not done yet. We just built a non-Hamiltonian graph. So how do we make it satisfy enough extension axioms? What we do is we blow every vertex into a potato, big potato of R vertices, and we put random edges between any two potatoes. So we're making a random lift of the graph. This is a standard construction. It was used by Erdos in one of his papers on random graphs, early papers. So you blow every vertex into a potato or fiber or whatever, and you put random edges between all the fibers. Now the crucial property that this has is that if you take any k-1 points in this graph, then there will be one extension, one common neighbor. And this follows easily, because if you take k-1 points, if you take all these k-1 points, then anybody here will be a common neighbor, the satellite. And if the k-1 points take one of the satellites, then anyone inside the clique, which must exist because you're only using k-1 and you're already using one of the satellites, anyone in the clique will be a neighbor of everything. So every k-1 points have a common neighbor, and this is enough to guarantee that the lift will satisfy all the extension all the extension axioms. Because the lift, what it does is it guarantees the extensionality, but also the non-extensionality. The fact that there is some guy that is not a neighbor of everybody. In the same, by just a simple probabilistic counting as we did before. Okay, so this is a very simple construction. And it has one consequence, which is from the fact that by the same argument that we just did here, because every IFP property that holds almost surely must be implied by some extension axioms, it also implies the following. For any IFP formula that holds with probability 1, it will not entail Hamiltonicity. All right, so this means that there is no IFP formula that explains Hamiltonicity. This is pretty good. I like this interesting non-negative results that hold with high probability like this. I think it's quite powerful negative.
In particular, it implies the inexpressibility results. None of these logics that are K-closed can express them.
Exactly, just follows directly from that. So now comes the other question about, before we move to the sparse case, still in the dense case P equals 1/2, there is this question of how do we compute the probability. And this has also a good answer. Fakin's proof doesn't give an answer, but the Russian's proof gives an answer. And this is basically a quantifier elimination argument that I had thought of giving here, but because I want to do other things, I will refer you actually to Blas and Harari paper that has a beautiful exposition of this quantifier elimination argument. And it's very nice to read it from there. So there's a second method. This would be for first order formula. What about IFP? Can you do the same? Can you decide what is the probability? And the original Blas-Gurevich-Kozin proof was also some kind of quantifier elimination, and therefore also give an algorithm to decide it. However, the algorithm had an exponential blow up in space, and there is a reason for that, as we will see. But there is a third method that I haven't seen written anywhere, but it's quite simple, and I want to tell you what it is. It's the following. So it works for both. The only thing you need to do is to evaluate the formula on a on some k extendable graph for k large enough, namely k bigger than the number of variables of the formula. And the reason this works is that, well, it's the usual one. It's that if it has probability 1, then it has this equivalence class inside. Yeah. So, okay, so it's clear that it works for the same reason that the 0-1 law holds. It's enough to evaluate it like this. And this requires the k extendable graph. And, well, you can find one by just throwing, coins at random. With high probability, you get a k extendable graph. But even explicit constructions exist. And these explicit constructions are exponentially big only, so 2 to the k. It's not too bad. And so also another, by again, Andreas gave a proof that the Paley graphs, the classic Paley graphs, actually satisfy the k extendable property. So the Paley graph has 2 to the k vertices, approximately 2 to the polynomial in k, and it satisfies all the k extension axioms. There is a more recent explicit construction that is purely combinatorial and doesn't use the number theory that is behind the Paley graph. Another thing to say is that these graphs are explicit enough that this algorithm will be competitive to the algorithms that come out of here. In particular, the algorithm can be done in polynomial space, even though the graph is exponentially big. It's exponentially big in k. Because it's explicit, you can actually run through all the vertices and check the quantifiers. And also, the edge relation can be checked in polynomial space itself. So in fact, you can do it in polynomial space for first order logic, because evaluating first order formula on a structure is a polynomial space algorithm. And a log space actually, but log space of exponential is polynomial space. And for this one, you get an exponential time algorithm. And in fact, you cannot do better than that, because in the case of first-order logic, Grandjean realized that it's not only p-space, but even p-space complete.
The p-space hardness was not what Grandjean did.
Yeah, that's right.
It membership in p-space. Because the p-space was from Stockmeyer, as we saw here, right?
Yeah, p-space hardness just follows from the theory of equality, so you don't need even the relation.
But he had a different algorithm. He had an alternating polynomial time algorithm.
Different from these three that I just said. Thank you. The exponential time completeness was proved by Blaž-Gurevich and Kozin, and this requires... actually, no, the hardness is again could follow for free from, even though this is not how they do it, it could follow from free from the theory of equality. All right. Okay, so now I want to talk about the sparse case. So this was the random graph with constant edge probability. And this was the case that Gilbert was interested in. And here I want to look at these two cases, which are by far some of the most studied cases in random graph literature. This one in particular is the one studied by Erdos and Reni in 1959, the first paper. So notice the number of edges you will have on average for if you have C over n, because you have n square edges, you have a linear number of edges in this case on average. And here you get n log n edges plus linear term. All right, so let's focus on this part, which is this is actually the threshold of connectivity, and it's a very interesting thing. So we think of C as a constant and n going to infinity. So here, the basic tool here is, again, in addition to the inclusion-exclusion principle, first and second moment, another basic tool is the Poisson paradigm. And again, I want to say that, so maybe this is the right time to say that. All these arguments of 0-1 laws, they all followed from just computing the probability of the extension axioms, and that we only used the first moment, right? It was very simple computation. So what this is explaining is that when you compute the probability of a first-order formula, that explains why you are always resorting to the first moment, because after all, that's the only thing you need. Right? So this is the power of these meta-theorems that say that all first-order formulas, computing its probability, even approximating it, just follows from first moment. So I think this is of value. These sort of theorems, these sort of statements are of value to understand what's happening. So now I want to claim that in this other context of sparse graphs, the only other thing you need, at least for first-order formula, is the Poisson paradigm. And indeed, you look at books and papers, and this is what they use all the time, right? When they look at first-order properties. Okay, so what's the Poisson paradigm? You have a bunch of random variables, 0-1 valued, and they have some small expectation, lambda over n. You should think of lambda as a constant. So these are rare events. And now the conditions of the Poisson paradigm, this is an informal statement. It says that if these events or these random variables are nearly independent, and nearly I'm not defining, and n is large, then this sum is going to be approximately Poisson. It's distributed like a Poisson random variable with parameter lambda. Now nearly independent, I'm not defining, but I don't need to define it. It just means the intuitive thing that the probability of the product is close to the probability of the joint event, of all the events happening. All right, so what is the Poisson distribution? Well, what does it mean to approximately be Poisson? It means approximately be Poisson. So the probability of being I is just the Poisson distribution. And this can also be made formal. This is the Poisson paradigm. Let's give one example, which is illustrative. And it's the same example as before. All points have at least one neighbor, and it so happens that the probability of that is this beautiful quantity. So how do we prove that? So let's look at the event for fixed n and u, the event that u does not have neighbors, and this is again this quantity. It's 1 minus p to the rest of neighbors by independence. And now, this, if you look at the probability, the expression, you plug it into this p, and you use this usual approximation when x is small, which is the case because p is small. Remember, n goes to infinity. then you plug this in and you get this quantity. All right? So these events are rare events, and you think of this as lambda. You have lambda over n, so you have 0, 1 random variables, whether it have a common, it has a neighbor or not. Yeah. So you can apply the Poisson paradigm, and the near independence is not obvious, but it's true. So you can apply the Poisson paradigm to these indicator random variables with these parameters. So you get that the probability of not having neighbors is distributed like Poisson, and the probability of a Poisson being 0 is this quantity. So the Poisson paradigm gives you what you want.
When you were talking about some paradigm, did you make explicit what you mean by near independence?
Yeah, I said explicitly that I don't want to say what it is.
Sorry.
It means the intuitive thing that the probability of several variables being 1 is almost equal to the product of the probabilities. And that's enough. If you have that uniformly, then it's enough to. All right, so here is an amazing convergence law for first order logic. I call it amazing because the first time I see it, well, the statement like this is not that amazing. What comes next is the amazing part. So the property says that if you have a first order definable property and you look at these varying probabilities of this shape with parameterized by this C, which is the C, remember, I mean, this parameter, this is the case of Erdos-Renyi. This is the one they were looking at. Then the probability exists. Moreover, the probability is a finite sum of terms of this kind where lambda is e to the minus c. Okay, so this is quite impressive. You describe exactly how they look, the probabilities. And so when I first saw it, I said, wow, how do they do that? I mean, this is a first order formula. It's quite complicated, and they can do this for any formula. But then the beautiful thing is that the proof is very illuminating, and once you understand the proof, then it's no longer amazing. I mean, it's the most natural thing. It's really natural. I mean, this is one of the examples where proofs really explain things. I mean, it's not. I mean, students don't really believe this, right? Why do you do proofs? We don't need proofs. I just believe you. But then that's, I find it quite annoying. I mean, look at the proof and you'll understand it better. All right. So at the end, I want to give a sketch of this proof if we have time. But now I want to go back to this notion of explanations. So do we have explanations here again? So here's an example of an explanation. Look at the property, some point has no neighbors, so an isolated point. Now, this implies non-connectivity. Right? If you have an isolated point, it's not connected. And the probability of having an isolated point is 1 minus the probability of not having isolated points, which we already computed, it was that. And it turns out that this happens to be exactly the probability of non-connectivity. And this is from the Erdos-Renyi paper. So this very simple sufficient condition, I'm not saying that it explains non-connectivity, it's too simple, but it explains the shape of the probability, and this I find amazing. So the question is, it explains the lower bound, and it doesn't explain the upper bound. Or does it? I mean, if you look at the proof of Erdos-Renyi, and it's very easy to read actually this paper, it's very well written, it's a fantastic paper. There is something going on there that might be possible to explain also the upper bound, maybe not by a first order condition, but by something else. And this is open. This is one of the questions I want to raise in this talk. So let's look at now the linear case. We have linear number of edges and expectation, and we look also at these things of explanations. So Lynch had another convergence law, and this was before actually the Thomas Spencer convergence law, and it says that if you are in this regime, then the probability exists. Moreover, the probability, and now as a function of C, right, it exists and it must be a function of C. It's the only parameter happening there, right? And the formula, of course. So as a function of C, it is a continuous function made of plus minus times e to the x, so the exponential C and real constants, or actually rational constants. So this is even more amazing, I would say, right? So you have these amazing shapes. So here is one example, that things that can happen in the first order world at this regime. there is some triangle. This property I made up. I cooked up a little bit from Spencer's book to have the shape that I wanted. So the property is there is some triangle whose vertices all have some neighbor outside the triangle that itself has no other neighbors. Okay, it doesn't matter whether it makes sense or not. What I wanted is to have a property that has this probability, and in fact you can make as many ups and downs as you like by alternating quantifiers. So in fact the probability of this property is this strange looking function, or not so strange, actually it's very natural. So let's go to more explanations now. Now at this level, C over n, can we explain more things? So there is this very famous business of sharp thresholds, right? So let's look at the property of non-tricolorability. It is known that there are constants CL and Cu, so that if you look at a random graph with approximately C times n edges, and C is below this constant, then the graph is almost surely not tricolorable. No, it's almost surely tricolorable, of course. So the tricolorability has probability 1, non-tricolorability has probability 0. And if it's dense beyond this constant, then it's almost surely non-tricolorable. And this is natural, right? The more edges you put, the more likely it is to be non-tricolorable. So you have this shape of probability. So the limiting probability is 0 for non-tricolorability up to some constant CL. And after some constant Cu, we have probability 1, the limiting probability of non-tricolorability. Okay. Here in the middle, it's a bit fuzzy what's happening, but it's conjectured that there is a constant, so that in fact this reaches here. And up to here you have 0, and beyond that you have 1. This is conjecture, it's not yet proved that there is such a constant. Anyway, so what I'm asking now is whether you can explain something from this picture in the sense of explanations, right? Like we explained connectivity, we explained the shape. Can you explain something from here? And it turns out that by first order logic, you cannot explain it, and there's a very simple argument. And it's the following. It's based on this convergence law of Lynch. So the question is, can you explain, for example, this thing up here that you have once when you're dense enough? By the way, some loose bounds if you care, but it's not really important. So for our discussion, it's not important. For the theorems themselves are important. So here's a simple observation. If you have a first-order definable property that implies non-tricolorability, which is a sufficient condition for non-tricolorability that supposedly is going to explain that, and it doesn't. It has probability 0. So and this is very simple from the 0-1 law. By the way, recall that you have probability 1, right? Beyond that. So here's the proof. It's very simple. By Lynch convergence law, this thing, the limiting probability, is a real analytic function of C. It was made of exponentials, plus, times, minus, no divisions. But we have zeros here, everywhere here. So because we have zeros and we have entailment, we're assuming that this entails that, then this is 0, so this probability must be 0 at all this interval. But then it must be 0 everywhere, because analytic functions, the 0 set of an analytic function cannot have, must have 0 measure. This is a known fact of analytic functions, one variable analytic functions. So this doesn't have measure 0, so it must be the whole thing. Non-trivial analytic functions have 0 sets of measure 0. So that's it. And this is using Lynch's proof. And I was wondering how I would prove this directly without knowing this structure of the limiting probabilities. And I was not able to do it, at least in the few days that I've been preparing the talk. So maybe it's doable, but I don't know. So this is something I wanted to share with you. And maybe I want to claim, some of you may know that a few years ago I studied random 3CNF formulas. So random 3CNF formulas. So these are CNF formulas generated at random. And this is a model of random structures that is not random graphs. And there what I proved is that so random trees in a formulas also have this kind of behavior. If you have a linear number of clauses below some threshold, then it's almost surely satisfiable. And beyond some threshold, it's almost surely unsatisfiable. So what I proved in 2002 is that there is no explanation for that fact that is expressible in data log. Right? And I claim, without proof, that it also holds for three-colorability. So I think I can go through the proof that I did in 2002 to show that this result also holds for data logs here. So there is no data log definable property that explains non-three-colorability. That explains this part of three-colorability. However, it's still open since then to extend this to fixed point logic, to inflationary fixed point logic. I think this should be doable, but nobody really looked at the problem. So,
Lynch had some papers on infinitary logics, right? Did it cover this case?
No.
This was released 95.
It covered the even sparser case. Yes. It didn't cover the C over N. All right. So now I have 10 minutes left. So I had this part of the discussion, and then the proof, the sketch of the proof of Lynch, not Lynch, but the Thomas-Spencer convergence law. I don't know, maybe 5 minutes on each. Let's see. Okay, so I see. So somehow this business of 0-1 laws and random structures and logic. I mean, it went very fast in the beginning, but then it started stalling, and somehow now it's not very active. And I think there are directions that can be followed, and they are interesting. And people should look more at that. In particular, this explanations business, I think we could say something more about it. So let me say 3 concrete things that we could try to look at. For example, on syntax. There's been a lot of work on trying to go beyond first order, beyond fixed point logic. For example, second order logic. There is beautiful work by Fauquion and collaborators on second order logic. However, there is a whole class of properties that are not covered and that random graph theorists are very interested in, which are properties that involve counting sizes of things. Like, for example, what is the size of the largest connected component? What is the size of the largest click in the graph, and so on and so forth. What is the chromatic number, when the chromatic number is not bounded by a constant like 3? So all these things you could do by throwing in counting quantifiers in your logic, but then very quickly you kill any possibility of 0-1 laws or convergence laws. So the challenge here is to come up with, design a language. I mean, we need to design some language that explains that gives some, that is useful for graph theorists, that explains what the graph theorists are doing, the random graph theorists are doing. In particular, here is an interesting, difficult question, but this is the kind of things I'm thinking of. It would be very nice to find some kind of logical limit law that explains the lower bound on the diagonal Ramsey numbers. So Erdos proved, it was the first use of the probabilistic method, that the number of vertices you need to find a k-click or a k-independent set in a graph, it must be exponentially big, right? And this was proved by choosing a random graph and then checking that it doesn't have such things. So it is proved, in fact, almost all graphs satisfy the property that Erdos needed. And however, the problem with that is that the size of the graph is something like 2 to the k, and you're looking at clicks and independent sets of size k. So this means that if you take this for n, then the sizes of the clicks and independent, well, I think it's something like k over 2, but it doesn't really matter, something like k. So it means that if you take n for the size of the structure, then you're looking at clicks and independent sets of size log n, which is not something you can say in any natural logic that we work on. But maybe we can throw in some device that allows us to talk about log n. So this is one question that might be possible to do by designing a proper language. I think this is an important question because, for example, we don't know explicit graphs that are of the kind that Erdos showed to exist. So maybe the logic could give something on that. Now about sharp thresholds. Okay, so there is this Friedgut theorem, famous Friedgut theorem, that says that in the particular case of three colorability, it says the following. It doesn't say that there is a constant. What it says is that there is a function. So this is a specialized, Friedgut's theorem is specialized to three colorability. It is a function so that if your probability is smaller than P of n, is smaller than that, then you're almost surely three colorable. And if the probability is bigger than that, 1 plus epsilon, over n, C star n over n, then almost surely you're non-three colorable. And what we would really like is to have a constant here, not a function of n. So what this function, we know this function is bounded by two constants. So it must. So the question is whether it converges or whether it goes crazy like that. So we cannot conclude that there is a constant because we don't know how it looks like. And the reason this is like that is because Friedgut's theorem is not uniform in n. For every n, it does a separate argument. And it is based on properties of the hypercube and of dimension n, and there is no way to do it uniformly. And this is calling for a uniform proof because you're looking at not an arbitrary property, but three colorability, which is quite definable. It's quite simple and quite nice.
So this on 3CNF, you would solve the problem with the exact sharp threshold, right?
Yeah.
That's what you're asking.
Yeah, it's the same as three colorability.
And there's recent results by Sly and others for KCNF where they get a sharp threshold, right?
Yeah, but k has to be large. So for k equals 3, their methods don't work. But in general, this would be an idea to try to make this inherently non-uniform argument, try to make it uniform and get rid of these annoying situations. All right. So about explanations, so explain why first-order properties appear as necessary or sufficient conditions depending on which context you are so often. And there is another example, which is the Hamiltonicity. It happens to be this is the probability, and then a first-order property aligns very much with this probability. Anyway, so this I don't want to say a lot more. So now maybe in the last 3 or 4 minutes I can tell you about this amazing proof and finish there. So in fact, when you see the proof, this is how it has to be done, of course. So the proof, this is from Spencer's book, Strange Logic of Random Graphs, or something like that. So the first step, there are 4 steps, I believe. You list as many almost sure properties as you can. So you throw in, so what are the almost sure properties of the random graph at this density? And this is very well understood. So for example, for every fixed k, there are no k points that induce k plus 1 edges or more. So in particular, every finite subset is unicyclic. It has only one cycle. There are r cycles of length k for any r and k. There are r points of degree k. All these things are true for every fixed r and k. And these are first-order properties. There do not exist k and k prime cycles at fixed distance. So if you fix the distance and sizes of cycles, then you cannot find that. In fact, I was thinking last night that this is a consequence of this. This is actually, I believe this is a consequence because you have 2 cycles in a bounded size set. But this one is not a consequence. It says that you cannot find 2 degree k, and this is exactly the degree k points at distance d. These are well-known properties, and also you cannot find a degree k vertex close to a k cycle. Okay, so let T be the set of all these axioms. This is like the part of the almost sure theory. Now let's describe the countable models of this. How do they look like? And this we need a drawing. So from these axioms that I described, this is going to look something like this. So you're going to have cycles of all lengths. And branching from this, you'll have infinitely branching trees. So these are infinite degrees. Branching from the cycles, you have infinitely branching trees, and these are components. They are separated. They don't merge. And you will also have vertices of degree k, whose neighbors will have infinite degree, infinitely like that. And this for every k. So degree k plus 1, and so on. This will follow also from this fact. There are no two things. I mean, these axioms guarantee that the countable models are like this. And then maybe you also have two more things. One is you may have trees of infinite degree and also isolated points. The models all look like that. Okay, so we described the countable models. And now we want to identify what is missing to make it into a complete theory. And what I claim that the only thing you need to make it into a complete theory is count how many isolated points you have. And this you can do by a pebble game argument, and it's not terribly difficult. So, and now you notice that these additional axioms which complete the theory, so any addition, if you add any of these, you have the theory, and you add this is complete. So, and these completions are incompatible. Because if you have I isolated vertices, you don't have I prime, if I prime is different from 1. And also they cover all the possibilities. Okay, this is because you have this Poisson distribution for the degrees, the number of vertices of degree or isolated vertices. And now you conclude that the probability must be then a finite sum of the additional axioms that make phi a consequence, which must be non-empty, right? Or it could be empty if it's totally false, for example. And this follows from a simple argument, just some kind of a simple limiting argument, and compactness. And then in the end, we need to use here something that looks like the Markov inequality. The problem is that it's in reverse. And the point is that here we're using that these are incompatible conditions, or these are disjoint events, and therefore this will actually work. The loss will come from the fact that this is an almost sure sentence. This almost sure sentence, you can forget about it by some small error that you're making, and then you get what you wanted. So the probability is approximated by a finite sum. And this is a finite sum of these properties, and these properties, you know the probabilities. They are the probabilities that come from the Poisson distribution. So this is the proof, and it had to be a bit fast because I'm out of time. But if you want, I can go a bit slower at some other time. Thank you very much.
Question? Just a question. In the previous slide, why is t plus phi I complete?
Well, you need to do a pebble game argument to show that if you have exactly the same number of isolated points, then the rest of the structure looks the same, because in fact these guys, you have infinitely many. You have not only one cycle of degree k, but you have infinitely many cycles of degree k. So in this part, you just play a pebble game, and the axiom is guaranteeing that the part that you could distinguish, you cannot. It's not a difficult argument. Yes.
So in random graph theory, over I guess the last decade, it's been very fashionable to consider random graph models like preferential attachment and things that have power law, the distributions and so forth. So do we know any 0-1 laws in that context?
Yeah, so there's a paper by James Lynch, leaks maybe 5 years ago or a bit more, and he considers their power law graphs. So some models that have this power law condition. I don't know exactly what he proves, but I know that he has studied this thing. Yeah, so the other thing is, your question goes a bit in the line of whether these graphs model something, and maybe we should make them. Usually the way I approach this is I don't really want to be modeling problems because I think of this as building blocks for other things. Like, I think random graph theory has been useful in other things that are not just the random graph itself. To develop techniques for analyzing other processes. And this logical approach explains that, so could explain that, so this would be nice.
Well, let's thank Albert again.